in the end, you get stuff. So it's I mean, it is like SYK, but unlike SYK, you don't have where the self-consistency is really crucial to get the exponents. Yeah, you get the right exponents, including self-consistency.
So change the thermal.
But then it's magically self-consistent, even with the prefactor and everything.
Okay.
Sorry.
Yeah, no, thank you.
Why do you have to use the averaging over
To justify the self-consistent equation as a saddle point. That's all.
That's it.
Previously, there was no, the whole self, people, that's probably why people didn't pay much attention to self-consistency, because the whole thing was ad hoc.
So in other words, you're saying the answer has actually been known for a long
Oh,
time.
yeah. The saddle point answer has been known. I mean, but it wasn't a saddle point. There's what we call the RPA theory has been known. And Sunsick pointed out that it was being justified by some other large N approach, that it wasn't justified.
Yeah, I thought the point was in that approach, it seemed to get corrections to it. No?
Yeah, well, it wasn't a large N saddle point. That's another way to say it. That if you computed higher order graphs, they were not suppressed by 1 over N.
Right.
But if you take the random coupling, they are suppressed by 1 over N.
I see.
That's the main point of our paper.
All right.
Which is kind of, yeah, it's amazing how simple it is. I mean, it's, yeah, I mean, it's, in that sense, it's in spirit parallel to doing things, showing that if you take CFT tools and average them, then you get a very simple 1 over, you get a gravity, there's a 1 over G expansion, right, in a way, or G expansion. Anyway, oh, what time is it? Almost 2 minutes past. All right, so good morning. Let's see. Okay, hopefully you can see me and I'm on the right screen. So we're back at Bloomberg. So a couple of announcements. So there's going to be a change in time in the US at the end of this week. So next week, we're going to continue at the same time in the US, which is 9 a.m. Eastern Standard Time, which will be 1 hour later in India. So please be aware of that. Can you hear me, by the way?
Yes, we can hear you.
All right, great. Okay. And then, so that'll be the next 4 lectures. And then there's a Thanksgiving week here in the US, where I will not lecture during that week. And the week after that, I'll be in India, in Bangalore. And I'll give 6 more lectures over there. At a time to be determined, I'm not sure exactly when. It may end up being quite early in the US, but you can be at home and watch it. Okay. Yeah.
So in your previous lecture, you discussed how you start from maybe some spin system and then go to the Spartan picture.
Yes.
And then get the, for example, Chern-Simons description.
Yes. Yeah. The chiral spin liquid.
Right.
Yeah.
Is it possible to just go directly to the Chern-Simons description? Because that's what you really care about, right? The very low energy description.
To go directly, I mean, you still have to solve the spin problem somehow. So another way to do it, which is, I guess, the way Laughlin and Kalmar did it, you take the spin problem and you think of spin up as nothing and spin down as a boson. So then you can think of it as a hardcore boson problem. And then postulated that the hardcore boson system should be in the nu equals 1/2 fractional quantum Hall state. Okay.
Yeah, I'm just thinking of theories like, for example, the CPN model, where you have an emergent gauge field.
Right.
There is a simple.
Well, that is exactly what we did, right? We wrote the spin in terms of fermions.
Yeah, no, I realized that, but there was the intermediate step of the partons. Well, anyway, it's just.
Yeah, well, the partons, I mean, the CP1 theory is also a theory of partons because the Z particles have a gate charge. It's also a theory of partons. The physical operator in the CP1 theory, the gauge neutral operators are spins, Z star sigma Z. So those are the spins. So,
okay.
So we're not doing anything different from the CP1 theory, in fact. Yeah, there's no gauge in the Z's are not gauge invariant objects. So similarly here, the partons are not gauge invariant. I had to put the partons in a Chern band to get the Chern-Simons term. But as we'll see today, you could equally well put them in a magnetic field and it'd be very similar. Yeah.
I also have a question from last time.
Go ahead.
This is the role of time reversal symmetry. Was it there microscopically and then was spontaneously broken, or was it explicitly broken? And if it is spontaneously broken, are there any consequences of that? Like two vacui.
Answer to your first question is it can be either. It can be either spontaneously broken or broken explicitly by the Hamiltonian. It won't make any difference to the theory of the phase. That's the phase where you have of the chiral spin liquid, you get exactly the same theory in terms of the quasi-particles and all their properties and the edge state properties. But if it's been spontaneously broken, well, there is a scalar which is gapped. And that only becomes important near a phase transition. So suppose there's a phase transition where the symmetry is being restored. And then you would have to worry about the fact that the time reversal was spontaneously broken. And there will be extra fields associated with, light fields associated with the fact that you're restoring the symmetry. So that would be an interesting quantum phase transition, which I haven't addressed. You first have to decide what the other phase is on the other side that you're going to.
Are there any?
But if it is spontaneously broken, won't there be domain walls where you have the different vacua on the two sides without going to a phase transition?
You're right. Yeah, there could be such configuration. Yeah. So that would be like going from Chern +1 to Chern -1. And yeah, then there'll be some edge states of the domain walls for sure. Yeah.
Okay, thank you.
What were you saying, Tom?
Exactly what you.
Okay, yeah, all right, yeah, that's correct, sure. All right, so we talked about this connection and which we've just discussed. Are there any other questions on the last lecture on the Chern insulator and the chiral spin liquid? I've updated the notes on a lot of that on the website, so please download the latest version and all the details on how the Chern number is quantized and how it relates to the Chern-Simons term or the Hall conductivity are in the notes. Okay. All right, so today I want to do the establish the same connection, but in a slightly different setting. This is the setting of the quantum Hall effect. So now you have electrons moving in 2 dimensions. They're not spins, they're electrons. They're allowed to move, so there's no local constraint that they have to be exactly, in the case of the chiral spin liquid, there was local constraint that the number of fermions on each side had to be 1. There's no such constraint. And initially, we'll just take free fermions moving in a magnetic field. That, of course, leads to integer quantum Hall states. And then we'll do a parton description and describe a few fractional quantum Hall states. And hopefully, given all the stuff you've already covered, this will be relatively straightforward, as you see, I hope. Okay, so we consider the integer quantum Hall case. I'm going to take h bar equals 1. This is important because many results are expressed in terms of h, not h bar. So always remember it's h bar, that's 1. Okay, so this is just a free particle and a vector potential. I'm going to use this particular gauge. Because that will be useful when we look at the edge states. So that's what I want to do today, is also explicitly show you in this case, it's a bit easier, as was shown first by Halperin, actually before TKNN, that there are chiral edge states on the integer quantum Hall system. Okay, so now we just go ahead and solve this equation. I'll be very quick about it. I presume most of you have seen it somewhere. It needs to Landau levels. So just to establish notation, we introduce something called, from the various quantities that you will see if you read papers on this topic, there's something called the cyclotron frequency, which in these units is EB/m. And there's a magnetic length, which is 1/√² of EB, and also 1/√² of m omega c. And then you can introduce a dimensionless coordinate in terms of the magnetic length. Y bar is y over L. And then if you take your wave function, psi, you can have a label n, and the function of x and y. Well, since you have translational symmetry in the x direction, it can be a plane wave in the x direction. And it'll be some function phi of n and k, which will depend on y. And this function just obeys the equation of the harmonic oscillator. So in appropriate units, d squared phi over dy bar squared. That's 1. Okay, I've gone ahead and also written the Eigen Energy because it's kind of clear. Okay, so just insert this ansatz in this equation, and this is what the Schrodinger equation becomes. This is the Schrodinger equation of a harmonic oscillator. But the key point here is a shifted harmonic oscillator. As you change the wave vector in the k direction, the center of mass of the harmonic oscillator shifts with k. So momentum in the x direction is the same as coordinate, roughly same as a coordinate in the y direction. So that's a very useful semi-classical picture to keep in mind.
Sorry, what's L bar?
Maybe it's L square, perhaps.
Yeah, or it's Y bar.
Let's get out. Thank you. Yeah, so KL is dimensionless, Y bar is dimensionless, so it's all right. Okay, so the very important property of this equation, which is different from the Chern insulator, is that the energy, the Eigen energy that the harmonic oscillator states, and here, of course, you can see that n is 0, 1, 2, it's an integer. The energy is completely independent of k. So you have a very large degeneracy of states. It's independent of k, there's no dispersion as a function of k. And that's very different from the Chern insulator, but it's a simplified feature. But in many ways, it's also a confusing picture because it makes the band flat and things like Chern number are not so easy to define. So you can imagine a more general problem that you added a very small theoretic potential here, and then it'll become exactly the same set of problems that you solved there, but then the algebra becomes more complicated and you have to learn Brock's theorem and all of that. Anyway. Okay, so then the question is, what is the degeneracy of the states? So this is the other important point. So if you take a geometry here, so let's know this. Make sure I have the same coordinate. Okay, so this is Lx, and this is Ly. So my k is some integer multiple x over Lx. And then the center of mass coordinate here, y bar, is, so the average of y is, of course, then minus KL. So the way you can think about this is that you have a whole bunch of states, and then you have states where k is positive, then y will be negative. So those are states that are running here with very large momentum, and then you have states with smaller momentum. Which, so this is just a basis of states. The larger the momentum, the more the negative y coordinate, and they're basically Gaussian functions about in the y direction. Harmonic oscillator functions. In the lowest Landau level, they're Gaussians. Okay. So another important point is that if you, well, occupy, say, the Landau level, so let's say here are the Landau levels, this is energy. 0, 1, 2, 3. If you occupy all states in the lowest Landau level, which is the most important case we'll be interested in today, then you occupy all of these states. And in fact, at any point in the center, the net current is 0. If you just compute it carefully, and it's done in the notes, that there is no current. So if you pick a point here, you get a current from here and there, and they all cancel out. This is just a set of bases that you've chosen to describe these states. All right, so this particular basis is very useful to figure out the degeneracy of states. The question is, how many states do we have here? The thermodynamic limit. Well, so the number of states, it's easy to count. It's the number of, so the question now is, what is the maximum value of n sub x? So what distance does n sub x, what are the values, allowed values of n sub x? Well, n sub x is given from here. So we know that k minus kl, or let's say kl is between 0 and ly. So let's just call this, so this distance is ly. So the range of y, which is kl, squared. So this is y bar, right? Thank you. Is that right? Yes. Thank you. All right, so then you get, ignoring things near the boundary, you will all get all of these states in this region. And so this tells us that the number of states here is combined into this, which is actually degeneracy. So the number of states is equal to Lx Ly over 2 pi L squared. And another way you can write this in the original units is the area of the sample times B divided by phi naught. And phi naught is the flux quantum H over E. So here A is Lx times Ly. So notice that's H, not H bar, and that gets rid of the 2 pi over here. Okay, that 2 pi comes from this 2 pi. All right, so that's the degeneracy of the states. And another very useful thing we're going to define is the filling factor. Which is, in this case, it would just be an integer. We will consider a fractional value, in a bit. So let me make sure I get the right. All the factors of 2 pi. This is absolutely crucial to get this right for this lecture. So I want to make sure I have it. So mu, the filling factor, is defined as mu, which is rho over p over phi naught, where rho is the number of electrons divided by the area, which is Lx Ly. Okay, so in the limit, you have a very large sample, then you don't have to worry about the edges, and all these results are exact. And so nu measures the density in units of the number of flux quanta. So that's one very easy way to remember it. And it's inversely proportional to P. Okay. All right, so then.
You're not considering the spin of electrons.
No, yes, thank you. So no spin in this entire lecture. So we assume you're in some very high magnetic field and the spin of the electron is polarized. Of course, there could be other interesting states where you're worried about the spin. Okay, so we'll be interested now in the case where nu equals 1. All right, so let me, so let's consider nu equals 1. And now, in fact, I'll write down the wave function. Now you can write down the wave function if you wish by looking at occupying all these states at n equals 0 for nu equals 1. And that will give you plane waves times Gaussian, and you'll get a big determinant to write down the full wave function. But it's very useful for later purposes, at least briefly, so we can connect with a lot of other work to write the wave function in a different gauge. So we choose a different gauge where A, instead of having this value here, we're going to now choose A is -1/2 R plus B. So this is going to be a different gauge here. Then all the lowest Landau wave functions, n equals 0 wave functions, become very simple. They become analytic functions of z, psi of z, which is proportional to z to the m times e to the minus mod c squared over 4, where z x plus iy. So in this particular gauge, which is, explicitly preserves rotational symmetry in a sense, or angular momentum, the wave function has this very simple form. And m is an integer, and in fact has to be positive, so on. And so these are the so-called circular states. The n equals 0 is just a Gaussian, and then you take higher and higher values of n, you get states which go farther and farther and farther out. So if you fill up a lot of these states, you'll get a sample which is the shape of a disk, rather than here, which is the shape of a string. Okay. So one very interesting result here is what is the actual wave function? So suppose I fill up all of these states in the lowest Landau level. What is the wave function size of z1, z2, all the way up to zn, and is the number of particles? Well, each particle will give you the same factor here, so we don't worry too much about that, but they have to have different values of m. So the answer will be the Slater determinant, it will be product on I e to the minus zi squared over 4, as the determinant of 1, 1, 1, 1, 1, z1, z2, z3, z1 squared, z2 squared, and so on. And that's the determinant to fill in the lowest n m values of these single particle states. Okay, so that determinant is called a van der Waals determinant. It has a very simple expression, which will be, of course, much more useful in the fractional quantum Hall case. So you can just evaluate that determinant and write a much simpler expression for it. So that determinant is psi. So this is at mu equals 1. The wave function product on I e to the minus zi squared 4, and product on I less than j of zi minus zj. So this expression here is identical to this expression, the Slater determinant. This form seems to suggest there's some correlations between the particles, but it's product of pairs of particles. This one makes it clear, well, any correlations there are purely due to Fermi statistics and nothing else. And why is the determinant equal to this? Well, it follows from the fact that this is a polynomial of a certain degree. And this polynomial vanishes anytime any two of these z's are equal. So when z2 equals z3, then these rows become identical and the determinant vanishes. And if you just count the degree of the polynomial, which vanishes at those points when any pair of points is 0, then this is the unique polynomial that has that property. All right.
I'm a bit confused. So this is the wave function for what? For n electrons, or
Yes, n electrons.
or n times m.
No, they have n electrons. There may have been too many n's here. N is the total number of electrons.
And each electron is n equals 0, and that's some value of m.
That's right. So the electrons are from m equals 0 all the way up to m equals n minus 1. So this wave function, if you actually look at the density of particles, so you look at the density, average value of the density, for this wave function, you can compute it on a computer if you wish. So it's of course angularly symmetric. It has looks something like this. It's essentially flat here. The density here is rho, but it has an edge. And at the edge, it goes very exponentially down to 0. So that takes a little work to prove it, but it can be proven. Take the modulus square of the wave function. This becomes the statistical mechanics of a Coulomb gas in 2 dimensions with log interactions, which is the Coulomb interaction 2 dimension. And from properties of the electrostatics of charges in 2 dimension, you can prove this as well, that this wave function, even though it doesn't look it, is actually a state of uniform density, except right near the edges. Okay, so this distance here, well, it's whatever the distance you need to, we call this r, then pi r squared times n, not pi r squared times the density must equal n number of particles. All right.
And rho is inside is the density of a filled band.
That's right. Rho is this density here, this value. Of course, here the density will look rather different. It'll be the same in the center, but on the edges it will fall off, and we'll have the rectangular shape. If we took those states, here you get a circular shape. Okay. All right. So what I want to consider next then is I'm going to go back to this rectangular shape and look at the edge states. We go through the computation by Halperin. Okay. So now we are back to the other gauge. So we're back to the gauge. A equals minus by and 0. And I'm going to consider the Hamiltonian. H is equal to minus 1 over 2m. Okay. So and now you'll see why I choose that particular gauge, because I had a potential in this direction. So there are walls or something towards the ends. So it's a very slowly varying potential in the bulk of the sample, but towards the edge, you have a boundary. But I still have conservation of momentum in the x direction. So if I write down the Schrödinger equation now, minus 1 over 2m, and now I'm dropping the bars here, L is equal to 1. I'll just take m plus, I'll have 1 over 2m of k plus k is the moment in the x direction plus by squared as we had before, but we now just add on the potential v of y. Will be some Eigen energy, which will now depend on k times phi n of phi. Okay, so this is still a one-dimensional Schrödinger equation, and you could have taken v of y equals just a quadratic function of y, and it's still solvable. You can do that, but let's just look at some general features. So what this En of k looks like. Okay, so let me make a plot. This is the tree plot here, and hopefully I've got my coordinates correct. So if this is y and v of y. So I'm just going to look at the right edge of the large y, the top edge of the sample. No, my y was this direction, wasn't it? I forget. Yeah, so this is the right edge. Anyway, so it'll be flat, and then let's imagine it goes off to infinity. And somewhere here, maybe I'll choose my coordinate y to be over here. So that's what v of y looks like. Okay. So here I'm going to plot the Eigen energy. Okay. And this is momentum k. So what's going to happen? Well, when k is very large in this direction, we see from here that y on the average is large and negative. So when you're out here at very large k, the wave functions are sitting over here. The v of y is just a constant, or you can even make it 0. So v of y plays no role in this region, and your Eigen energy is at exactly the Eigen energy you already determined. So here you're going to get at very large k, the good old Landau levels that you had before. They'll be k independent and flat.
Why? What happens at large k? Why can we look at y's that are large and negative?
So we're looking here. Okay, let's go back here. For y large and negative, it's just v of y is 0. Okay, so now you're going to have to solve this harmonic oscillator equation, and the wave function of the harmonic oscillator are centered where this is 0. And that's centered at k equals minus by, which is, since y is large and negative, it's k is very large. Okay. So if you're sitting here in k, then your wave function is some sort of Gaussian here. And it doesn't care about the fact that v of y is going to move up. So as you decrease your values of k, and you come down to smaller k, this Gaussian is going to come here, here, here. And now you can see it's going to go up, and the energy is going to become k dependent. So as you decrease your k, you approach the edge of the sample, and your energy goes up. Okay. So that's really all there is to it. So all of these things will go up in a way that roughly mirrors the increase of v of y. So this is roughly what it looked like. Of course, you can do a better job of solving it. And you get these states here that move on up as k becomes smaller and smaller, because you're hitting the edge of the sample in the y direction. Okay, is that clear? All right, so now, still dealing with free electrons, we started in a state where we fill the lowest Landau level in the infinite sample, but we have some chemical potential here. This is our chemical potential mu, and we're filling all states below that chemical potential. So what we see now, so these states are all occupied. These are the low energy state. All these higher end states are not occupied. But now we see something very interesting. In the bulk of the sample for large K, which is the same as sitting over here, there's a gap. Now to create add any extra electrons, I have to go all the way up to the next Landau level. But as I approach the edge, well, I have a Fermi point, and I have a 0 energy excitation. So I have a low energy excitation on the edge. And in fact, this is exactly the chiral Fermi gas that we saw last time for an insulator, where we had, I showed you the picture of the bands, which is now on the website actually, where the bands appeared, the one-dimensional band appeared within the band gap. Here you can explicitly see these one-dimensional bands. Here's one of them. And the other one is at the other end of the sample, where you have the other edge. But I'm only showing one edge here. Okay, I don't have to worry about the other edge because the wave functions are Gaussian localized on the magnetic length scale. Okay. So what is the state over here? Well, it disperses as a function of k. So that means it's moving. It's got a velocity, and it's moving in the x direction. Okay, so if I draw my sample again, so I think this was y. Yeah, this was the y direction. This was the x direction. So I have a state on. So what I hear. Let's see if I get the sign right now. So this thing has a velocity that's negative as k increases. So, and this is on the right edge. So that means the thing is flowing this way. I have a state over here going this way. And on the other edge, I'll have a state going the other way. So this state over here is a bunch of wave functions that are moving in the negative x direction on the positive y end of the sample. And similarly, in the other edge, there'll be a bunch of states moving in this direction. Okay. So I can now very easily write down a theory for these edge states. So Lagrangian for edge states. Well, it's exactly what we had last time. Psi dagger, back in tau, minus I VF, d by dx, psi. So it's a 1D gas, because it only disperses in the kx direction. There's no dispersion in the y direction. And it's, states that are sitting at the edge of the cell. And they're exponentially localized in the transverse direction. Okay, all right. So this is all very explicit, and you can see them appear without even knowing anything about Chern numbers. Now, these edge states are really important in this case for physical properties. If you now put a voltage and you drive the current to the sample, then, as I said earlier, the states in the bulk of the sample carry no current. But these edge states certainly do carry current. So you can drive current and the current will move downwards on this edge and upwards on this edge. So any transport properties at low enough temperatures, especially the Hall conductivity, is completely dominated by the edge states. And you can compute the Hall conductivity of these edge states. That's done in the notes. I won't do this here. And you find that the Hall conductivity, or sigma xy, is e squared over h. And the fact that it's just 1 times e squared over h corresponds precisely to the fact that there's exactly one edge state here. If you raise your chemical potential and you started getting edge states, the second edge states, then you'd have a transition to a state which has sigma xy is 2 e squared over h.
Subir, how did you derive this Lagrangian for the edge states from the Landau levels?
Well, so the only thing I need to know is the velocity, and the velocity is just the slope here. So the slope of this curve, the EdK, is the velocity. So I have to solve this equation. I have to get the energy dispersion. I determine the velocity at the chemical potential, and that's the only parameter I need to know to describe this one-dimensional gas.
And psi dagger would refer to
so this is some quantum field here, a fermion field, which is living on the edge. And it has so psi is a function of x only. Now it creates a particle. Psi dagger creates a particle that lives on the edge, lives over here. It has like a Gaussian shape in this direction. And it's a plane wave in that direction, the y in the x direction.
Understood. And the equivalent case for the bulk would not have this V term at all, right?
No, the bulk has a gap, so you wouldn't be writing it down in some low energy theory for the bulk. You really have to go back to the full Landau levels, and there it costs a finite energy to add or remove any particle. Right at the edge, it costs 0 energy to add or remove a particle, and that's the only set of particles I'm focusing on. So all of the particles I add on the edge have a Gaussian wave function in the y direction. So I know that, I just integrate over that. And there are plane waves in the x direction. So then this is the Lagrangian that describes plane waves in the x direction.
Thank you. Yeah.
There's free particles moving only in the x direction or the minus x direction, depending on which edge you're at.
Shapiro,
Yeah.
two questions. So I know the conductivity is going to not be affected by putting in interactions and disorders.
Yeah.
What about VF? VF you computed from this
Yes.
Fermion
Yes.
calculation. VF is some parameter that gets changed if you put in interaction, right?
Yes, so that's a very good point. So related to what I was going to say, thank you, Tom. So first of all, you put in lots of interactions if you want, take a general theory. Then you will certainly renormalize the value of VF. And you could also get interactions between these fermions moving along the edge. You could also put in some disorder. Suppose there's some impurities here. Maybe let me talk about those. So there's a few impurities sitting here in the bulk of the sample. Well, so the point is, first of all, those impurities don't change the conductivity. And why is that? Well, because because the state is chiral. The particles are coming in. Well, maybe they'll go around the impurity. No problem. It'll be, they'll still be moving in the same direction. But they never get backscattered. There's no way for them to go in the other direction. So there's zero backscattering. The impurities don't matter. There's also interactions here you can add. It's relatively easy to see that they don't matter because 4 Fermi terms are unimportant at low energies in one dimension. The other interesting fact, even the velocity doesn't matter. And that, I would say, goes back to the Landau formula for transport. What Landau showed that if you just took, just an ordinary one-dimensional conductor and computed its conductivity, the Landau formula is that the conductivity is E squared over 8 and the trace of the transmission matrix. Even for a free electron gas, the velocity cancels out. It doesn't appear in the conductance. And so in the Landau formula, the transmission coefficient is 1 because there's no way to get backscattered. So that ultimately, those are the arguments that ultimately justify that this is, quantized and in fact now used as a way of measuring the value of the fine structure constant.
So the other question I had last time,
Yeah.
you did a similar analysis, but you actually got the wrong answer by this analysis, right? Because there was this factor of 2 that came from the fact that it's level 2 current algebra.
Oh, well, so that here I don't have any gauge fields here. Right. So there I had a gauge field, which leads to very singular interactions, which we will get in the fractional quantum Hall effect. So you will need those gauge fields to move away from this integer value. Here I'm just talking about ordinary Coulomb interactions, which are typically screened anyway on the edge. So they're not as singular as the gauge field. So we will need the gauge field if you want to move away from integer values. Okay. Any other questions? I have many other topics to get through, and I could certainly say much more about it. And there is a fair bit more, including explicit calculations of this in 2 different ways, using either the bulk approach or the edge approach. In both cases, you get the integer answer. The edge approach is much more instructive because it's really what you need to understand the generality of this result. How it has no corrections whatsoever.
I have one naive question.
Yes, please.
At this level, can I see from the theory of the edge that a bulk is required for it to exist?
Yes. So that I guess it goes to these so-called anomaly inflow arguments. And I know I keep saying this, but that is also in the notes. So if you take this theory and couple it to an external electromagnetic field, then you'll find that the Chern-Simons time term that that you induce by considering the effects of the edge fields can only be fully gauge invariant if there's also an edge Lagrangian like this. Yeah, so right.
Another way to see it is if you just couple the electromagnetic field to that.
To the edge.
Anomalous.
It's anomalous. Okay, thank you. Right. Yeah, which is, I guess, what Nadi was also objecting to last time. Yes. Okay. All right, so now I think that's really all I want to say about the integer quantum Hall effect. And now we can jump ahead to the fractional quantum Hall states. Any further questions?
One small clarification.
Yes, please.
It's a more of an intuitive question. The way you derived it, it looks like the current really flows on the edge.
Yes.
But it also needs the other edge, the bulk. So is there a sense in which the current flows also in the bulk, or is it only, or is it always the case that it's only on the edge?
It's always on the edge. I mean, you can measure the current. You know, people can come in with various probes and see what the current is, and you can see it's only on the edges. Yeah. So there are states in the bulk that, if you take any given state, you'll see there's some current. But when you sum over all of this occupied state, the net current is zero.
I see. Thank you.
So, and in fact, the Hall conductivity is, you know, to drive a net current, you have to have the current here is not exactly equal to the current there. So there's a difference, and the net current that you will be driving the sample is the difference of the left and right currents. And from that, and using a few general arguments, you can then see why there's a Hall voltage that will develop in the other direction. So that's why the linear, in the end, the linear conductance of this edge theory is in fact related to the Hall conductance of the whole bar. So yeah, there's a lot of literature on that with using the Landau-Whittaker approach to all of this, and that's essentially exact. All you need for that is, you know, the various leads on your sample, and at very low temperatures, the transmission coefficients of all the edges. Of course, you can get, in some cases, in the fractional quantum Hall states, very exotic edges, which are non-trivial conformal field theories. And yeah, so we'll get to those in a minute.
Can you please say briefly what does one mean by an anomalous theory, or what does anomaly mean?
I'm afraid I can't, because I can't be brief, but the more important reason, I'm not sure I understand it well enough to talk about this. Maybe Tom or Nadi want to attempt an answer to that. No. Yes, Edward.
In one word, if you just look at this Lagrangian that you wrote and you add the gauge field and you try to integrate out the fermions, this is just a determinant, it's straightforward to integrate it out. The result you get is not gauge invariant. And that's called the anomaly.
I mean, that doesn't mean the theory is inconsistent. It just means that if you put an external gauge field, then the final theory will not be gauge invariant with respect to that external gauge field.
Yeah, it's not an inconsistency in the theory. Theory is perfectly consistent.
Okay. Yes, I do.
I was just going to suggest the following. Suppose you only have one edge. You apply an electric field, which accelerates the electrons and makes the Fermi level go up. And if you have only this one band that you're drawing, it would violate electric charge conservation. When the Fermi level goes up, the electron density goes up.
Okay, all right, okay. So I hope you could hear that. Okay, that's good, thank you.
Actually, I could not hear it well.
So what Edward said was that if you apply an electric field, then the Fermi level will move up here, over here, and therefore you get a net charge on the left edge. And the question is, where did that charge come from? So you end up violating charge conservation. So the charge that you accumulate on one side has to come from the other side.
Okay. Thank you.
Okay. Right, so now let's just jump ahead to the fractional quantum Hall effect. So I'm going to use the part-on approach. And this was, in this context, rather explicitly discussed by Jane very early on, 1989 already, around the time he wrote down the famous Jane states, which we'll also talk about. But strangely enough, it hasn't been used much in the literature since then. With the benefit of hindsight, I think this is the cleanest way to do a lot of things. Much of the condensed matter literature uses flux attachment transformations and dualities, and they can be highly confusing and often are not entirely correct. But this one, at least formally at every stage, is well defined. And it does actually give you a very compact description of the important quantum Hall states, particularly most of the ones that have been observed. So let me just discuss it. So what we're going to do, we're going to take our electron operator, which I'll call C and no spin here. And I'm going to decompose it into three fermions. The partrons, which are called psi1, psi2, and psi3. Okay. So you can imagine putting this on a lattice. So you can put a site index if you want. Eventually, I'll just work in the continuum. And this is just a very simple thing. On each side of the lattice, I have two states. I have the empty state, and I have the filled state with one electron in it. And that I'm going to just equate here also with the empty state. And this state I'm going to equate with psi1 dagger, psi2 dagger, psi3 dagger. So now if you really had three partons, then their independence, so the total number of states in my Hilbert space is 8 on each side. I'm going to declare all the other states to be illegal and demand that these are the only two legal states. Okay. So you could it's sort of like a repetition code. You're representing 1 by 1, 1, 1. That's all. And all other states are not allowed. Okay. So if you want to get this, these two states only, then you have a constraint, and the constraint is very simple. Psi dagger 1, psi 1 equals psi dagger 2, psi 2 equals psi dagger 3, psi 3. So if I impose these constraints exactly, then I will exactly restrict my 8 states in the Hilbert space of the 3 partons to these 2 states. These are the only 2 states that satisfy both constraints. So I only need to impose 2 constraints. There are also other constraints which are implied by these. For example, like psi 1, psi 2 equals 0, or psi dagger 1, psi 2. So these are implied by these, but if you may want to impose them explicitly, in particular, you can see that there's a certain SU3 symmetry here, and if you want to make everything SU3 invariant, then you probably want to impose those constraints too as you go along. But we're not going to bother with that because just imposing these 2 constraints is sufficient. And so let's just stick to that. And we're going to only work with U1 gauge field as you might expect, rather than SU3 gauge fields. But if you insist, sometimes you could work with SU3 gauge fields, and then you can get even more exotic states that could be important for certain non-abelian states if you care about them. But at this point, let's just stick to the U1 case. So now the point, of course, here is that if you have this constraint, then you have a gauge symmetry, just like we had for the spins. So I now have 2 U1 gauge symmetry, U1 cross U1 gauge symmetry. which I will take to be psi 1 goes to I rho 1, psi 1, and psi 2 goes to e to the minus I rho 1, psi 2. That's gauge symmetry 1. And the other one, and here will be psi 3. Oops. Okay. So if I could just assign psi 1 to have a positive charge in the first gauge field, then psi 2 will have a negative charge. And if we get psi 2 positive charge in the first gauge field, psi 3 would have a negative charge. Of course, there's many ways of choosing it, and okay, there's one way. All right. So now what you should really do, just what we did for the spin system, is you want to take this ansatz, put it into your actual Lagrangian or Hamiltonian for your fractional quantum Hall states or whatever. And then you'll get very complicated terms like C dagger C will become a 6 fermion term. Previously, the spin dot spin became a 4 fermion term. Here this is even more complicated, 6. So you get some very complicated Lagrangian. And then you imagine that you have some saddle point at which these gauge fields are not fluctuating too strongly. So you take some mean field saddle point. And then you do all kinds of Hubbard-Stratanovich decouplings to write down a simple theory for the partons in the background of the saddle point. Now, all of those steps we laboriously went through for the Z2 spin liquid anyways, and maybe partially for the chiral spin liquid. But hopefully you're all experts at it by now. And so we'll just skip all the steps and just write down what the general structure of the effective Lagrangian should be, just from gauge invariance. Okay. So in this case, we are assuming that everything is, if you to make this rigorous, you probably want a lattice. But let's assume everything is happening on a much longer scale. Everything is long wavelength on the lattice scale you use to define these states. So what would the theory look like? So I will have 2 gauge fields. Which let me see. Since I can use it in a minute, what did I call that? Okay. Oh, the B. All right. Sorry. So I have 2 gauge fields, B1 and B2. That's unfortunate notation, but small b will refer to gauge fields and big B will refer to magnetic fields. Okay. So what would the theory look like? So you would have, let me just write on the spatial terms. So the most important one. So we'll have B dagger 1. Oh, sorry. Psi dagger 1 over some coefficient times grad minus, so psi 1 has a charge, so minus IB1. And let's put the external field on to act fully on psi 1. It's up to you where it acts, but let's put it on psi 1. And then I'll have psi dagger 2 of grad plus IB1 minus IB2 psi 2. And I have psi dagger 3 of grad minus IB3 B2, sorry, of psi 3. And various other terms. And really, since we're not trying to do a microscopic theory, we're not going to try to write that down. Just the statement is whatever you write down, it's invariant under these gauge transformations. And of course, the gauge transformation B1 goes to B1. And I want to get the sign right. Minus, I guess, minus grad of rho 1. And B2 goes to B2 minus grad of rho 2. So you have these gauge invariances here, and this gauge invariance here, and you just write down all possible terms consistent with these gauge transformations.
So So
Yeah.
here what you're saying is no matter how I distribute the real charge
Yeah,
among those three sides, you can reabsorb it into the B fields.
correct. There's a, that we can redefine your B1 and B2 so that you can put the charge anywhere you want. Yeah, so I just chose to put it there. Yeah. You can put, I don't want to take fractions, well, because these are compact gauge fields, in some cases that's important. So you don't want to put factors of 2. But with the external gauge field, you could take fractions, but even that's a little uncomfortable. So if you don't want to put A over 3, A over 3, A over 3, then you have to keep track of, you know, the flux quantum. It's become a little more careful. So it's better to put it in one place. Okay. All right, so this is our theory, or this is just a general theory of electrons in any dimension. I mean, so far I haven't made any particular specialization. You could do this, if, you know, whenever. You could always do this for any system. But of course, the question is, when is this a useful thing to do? When is this particular fractionalization something that's likely to happen? And I suppose that's probably why the Parton method has been used as much. It's very powerful, but it doesn't tell you when it's good to use it. Other methods or numerical methods, you know, somehow motivated from this particular Hamiltonian. But once others have motivated or experiments have seen a certain state, you can just go ahead and figure out what's the right Parton description that will give me that state. So when do we use this? So we want to use this in the following situation. Okay. So we have an external, so we're going to be in 2 dimensions. We have an external field B. And I'm sorry, the electric charge has gone, we've absorbed, okay, just for simplicity. And now these partons are going to experience their own magnetic field. So the magnetic field on psi1 will be, I'll call it B1. And B1 will be, you know, del cross A plus del cross B1. And parton 2 will experience the field B2, which will be del cross A, del cross B1, B2 minus del cross B1. And B3 will be del cross minus del cross B2. And of course, now you should check that B1 plus B2 plus B3, the net field is equal to the external field. So each of the partons experience a net field, and this I'll put a bar here because we're going to imagine that these gauge fields have a non-zero expectation value in the saddle point. These are fluctuating fields here. This is their average value. Okay, so when should this be useful? Well, when it's useful is if the parton fluctuations are weak. And so when will the parton fluctuations be weak? Well, if there's a gap to parton excitation. So in a magnetic field, so what we require is B1, B2, B3 such that psi1, psi2, psi3 occupy N1, N2, N3 Landau levels. They fully occupy their own Landau levels. And then you'll have a gap. So then there'll be a gap to all the excitations of psi1, psi2, psi3. And there's a hope that this very drastic decomposition is like at least stable. There's no gapless excitation anyway. You may have to worry about other things, but this is a good starting point. So what is this? So what does this imply? So now let me make sure I get this right. the density of the electrons is the same as the density of all three of them have the same density because of the constraint. This constraint right here, the density of the electrons is the same as density psi 1, psi 2, psi 3. So the filling fractions of each of them, so 1 over nu is equal to, where did it go? That's the magnetic field. What is it? What's the density? Rho 1. So rho over b over phi naught. That's the filling fraction of this. Filling fraction of the first fermion, which now is going to be n. It's going to be an integer. Is rho, which is the same as rho 1 over b1 over phi naught, and so on. Nu2 will be an integer n2, which will be rho over b2 over phi naught, and similarly 2 goes to 3. Okay. So I have this equation here. I have these equations here, and you combine them, and you get a very simple expression. Sorry?
The first one is nu, 1 over nu.
Oh, thank you. This is new.
The flux quanta are all the same.
Oh, yes, E is 1, yeah, and H is 1. Flux quanta is H over E, and of course, E equals 1. So there may be factors of E that you have to carry through, but okay, E is 1. We can always measure P1 in units of E. Okay, yeah, which is obviously what we're doing here too. We're just equating internal field to external field. So we put E equals 1. All right, so if you combine all these relations, you get a very elegant looking relation for the filling fraction of the electrons, which is 1 over nu is 1 over n1, 1 over n2, that's 1 over n3. So for this 3-photon construction to work, n1, n2, n3 are positive integers. In fact, they can even be negative if you put the field in the other direction. We won't consider that. Then this is the special filling fractions. And these are, special case of what I call the Jane fractions. And in fact, essentially all observed states are of this type. Okay. All right, so that's it. So now we have a saddle point, which has a gap. Then we can do all kinds of fluctuations about it. You'll get consignment theories, edge states. But we've done enough of all of that. In fact, the whole analysis will be identical to things we've already talked about, just with different cases of that. Okay, so what's the simplest case? The simplest case is n1 equals 1 equals 2 equals 3. So all of them equal to 1.
Is there a simple formula for the Chern-Simons levels in terms of these integers that you?
Yes, but I'm not going to do it right now. So it's a bit of a mess. I think I've only done a special case. So we're going to look at the case. First of all, the most important case is n1 equals 1 equals n2 equals n3 equals 1. When of course nu is 1/3, that's the famous Laughlin state. And now, if you go back to the beginning of the lecture, I can write down the wave function of this state. So the wave function of the electrons, so this is the capital psi of Z1 to Zn, is the product of 3 wave functions. It's the product of, let me say, a wave function of psi1, and this will have some coordinates, let me call them W1, And similarly for the other ones, product is outside. Wave function. Of the field psi 2 with coordinates W2 and 2 goes to 3. Okay. Now, what are these wave functions? Well, these wave functions, we already know that that was a simple Landau level. So this is product of W1I minus Wj. Let me not worry about the W1I minus W1j. And this will be product on W2I minus W2j. And this will be product of W3I minus W3j. This is the fully filled Landau levels, that the van der Waals determinant. And then you have a constraint that the densities are the same. So we have the constraint that Zi equals W1I equals W2I equals W3I. That's the original constraint that you had when you started out the proton construction. And of course, then this is the famous Landau Laughlin wave function. And I'll leave out the exponential factor.
You could satisfy the constraint with extra phase factors, right?
Well, these are the coordinates. The position of the particles wherever they are have to be the same. These are not.
But the real constraint is that the densities are the same.
If you apply that at every point, then the coordinates in the first quantized representation, the coordinates of the particle have to be the same. I'm kind of going back and forth with the second
Yeah,
one.
no, I'm just saying the individual wave functions could have factors that would disappear when you went to the density.
Okay. I'm not sure which factors you're referring to. Some things that appear up here. I think this is fine. I don't think there's any arbitrariness here. Yeah. Okay, so that's of course the Laughlin wave function that started this whole analysis. And then later on, Jane pointed out that, in fact, this is one very simple way to think about it. But then the power of Jane's approach, and so after Laughlin's wave function, there was a very complicated theory, I should say, at least complicated for me, of what's called the hierarchy, because the experiments quickly showed many other fractions. And so people developed a hierarchy. And the basic idea of the hierarchy was, well, you have the Laughlin state and it has certain quasi-particles, which have fractional statistics. All of that is very similar to the chiral spin liquid. And then those fractional statistic particles can form states of their own, fractional quantum Hall states at other density. So you get a finite density of quasi-particles about the Laughlin state, and then you get a hierarchy. Well, the hierarchy is nothing wrong with it, but it predicts all kinds of fractions, and only a small fraction of which are actually seen. And also there's the question that the hierarchy assumes, the whole structure of the hierarchy, at least initially, assumes that the quasi-particles are dilute. But to get the higher states in the hierarchy, you're making them quite dense. So should you really believe it? At least qualitatively you could, but quantitatively it may not be the right way to think about it. Anyway, so what Jane showed was that if you did this approach, in fact, it was highly predictive in the sense that the most important fractions are the ones where you just take one of these integers and make them not equal to 1. So more precisely, the other important cases are n1 equals 1, n2 equals 1, and n3 equals n greater than 1. So you put 2 of the partons in the lowest Landau level, and the others in some higher Landau level. Then if you take that famous expression and work it out, you get nu is equal to n over 2n plus 1. And these are by far the most important quantum Hall fractions. The next one will be n equals 2, which will give you 2/5 after 1/3, and so on. Okay, so how much time I have? So probably I'll have to say a bit more next time. So now there's,
And to get nu equals 1/5, do we go to 5 partons or do we get it?
the 1/5, yes, 5 partons, but that's a relatively hard fraction to see. It's pretty close to a Wigner crystal. Most of the ones that, experiments are around nu equals 1/2. Yeah. Yeah, but in principle, right. This also has its, plethora of possibilities. But what's nice is that the very simplest possibilities. The 3 is the smallest thing you could do. You can go to 1, then there's nothing to do. 3 is the smallest allowed number. And you just make one of them greater than 1, that's sufficient to give everything. So there's a certain economy here. But of course, it's in fact, all of the states in the hierarchy can also be obtained by this approach. Yeah. Well, I have 15 minutes, so what should I talk about? Okay, maybe I'll talk about edge states next time. Let me talk about one very important case, but there's a slightly different type of topology. So at this point, if you've been following my lecture so far, you just have to turn the crank and do everything we did for the chiral spin liquid and figure out the edge state theory, the statistics of the bulk quasi-particles and all of that. Just take that theory and you integrate out the fermions and look at the edge states, just repeating what we did for the integer quantum Hall state, but now with this gauge fields and so on. But let me mention here, and maybe I'll say a little bit about that next time, and then we'll be done. But let me mention here another very interesting case where you get some new types of states, which have no analog really with what we've talked about so far. So the one case is n goes to infinity. Suppose I take the n goes to infinity limit. And so your nu then becomes 1/2. So what this means is that the side 3 fermions occupy n3 infinity Landau levels. And what does that mean? Well, really, if you look at this formula here, if you're filling integers going to infinity, well, the way it goes to infinity for a fixed density is your B field is going to 0. So that means B3 is 0. And so the side 3 fermions move in 0 field. This is a whole new ball game. What do fermions, when they move in 0 field, do? They form a Fermi surface. That was chapter 1 of the course. So we would expect the side 3 fermions to not fill Landau levels, but will form a Fermi surface. So this is some Fermi wave vector here, kx and ky. And the volume enclosed by the Fermi surface, these are spinless. Well, that's pi kf squared. 4 pi squared is going to equal the density of electrons, because the density of electrons is equal to the density of side 3 fermions. So this is potentially a dangerous thing with the logic of what we've been talking about, in the sense that the side 3 fermions no longer have a gap. So now you can take a fermion from inside the Fermi surface and put it outside with arbitrary low energy. And so it's a gapless state, unlike all the states we've talked about so far, but at least in the bulk had a gap. This doesn't have a gap in the bulk. Okay, but now there's actually quite a lot of good evidence that this state is seen in experiments. It's called the Halpern-Lee state, so the HLR state. And it's a gapless quantum Hall state. So the whole procedure of edge states and so on doesn't really quite work here because you have gapless excitations in the bulk. But nevertheless, the gauge field approach, has seen a lot of, in fact, does work as we understand today. the gauge fields do have very strong effects now on the bulk, and they change the spectrum of these quasi-particles. And you get what we call a non-Fermi liquid. It's not a Fermi liquid like we started out with. And this is a topic that I will cover towards the end of the course. So, but this is one way you get a problem of fermions coupled to a gauge field.
The gauge field here is what you call B2.
Yes, so what will happen is, yeah, the B1, you can integrate it out. Now, if you, okay, so this is another important point. In reality, there's really two gauge fields, B1 and B2. And they have, B1 will have a Chern-Simons term that you can get from integrating out N1, the Psi1 and Psi2 fermions. Now, if you integrate out B2, which formally you can, then you'll end up getting Chern-Simons term with the improperly quantized in the bulk. So if you want to work with just one gauge field, then you have a Chern-Simons term that's not properly quantized. But you can fix that, as you and others have shown, by keeping more than one gauge field. And this formalism automatically gives you the right number of gauge fields you need to get everything properly quantized. Of course, in this problem, since there's no charge, there's no gap in the bulk, maybe it's not such a big sin to just work with one gauge field because you never have 8 states or anything like that. Everything's really in the bulk. I don't know. Do you disagree with that?
No.
Okay. All right, great. Okay, so you have fermions in a zero magnetic field here, which claim you form a Fermi surface, and then you see some, there are very good indication, in fact, of this particular Fermi wave vector. It's been measured in various experiments, in fact, here at Princeton by Mansour Shagan. This equation is observed to be obeyed rather accurately in observation of this state.
Sorry, the Fermi, how do you see the Fermi vector?
So you have to put an external perturbation which oscillates in space. And if it has a wavelength which matches this KF, you observe some sort of resonance. So you do a surface acoustic wave which has a certain wavelength, and the wavelength of the wave matches this wave vector, you see enhancement response and so on. Yeah, they're very clever experiments, and you can, the point is that these KFs are relatively small because the density in these 2D electron gases is quite small. For a KF and an electron gas in a real material, that kind of experiment would be impossible because the KF is way too large. The wavelengths are very short. So these densities, these wave vectors are, thousands of atomic spacing, so it's easy to measure them because of the way these 2 DEGs are created. Maybe hundreds, sorry.
That's driven by the applied physical magnetic field.
Yes, but also the way you create these 2 DEGs is by doping gallium arsenide, and the dopant density is rather low. It's a very small set of dopants, so the density of the electron gas is small, and then you need that also to fill an integer number of Landau levels, because if you took electronic densities that you would get in a crystal like cuprates, I think you would need hundreds of Tesla. No one can achieve those to get anywhere close to the quantum Hall regime. Right. So all of those go together to make these experiments possible, the low density and the relatively small magnetic fields that you need to impose to see highly quantum effects.
Did I understand?
Yeah.
You said that the Fermi liquid picture of this state is not exactly correct because the interactions are important.
Absolutely, yeah. But so that's right. So that's a good question. So what do I mean by a Fermi surface? Well, we introduced a Fermi surface for a free electron gas as a jump in the momentum distribution function. Then we found it's also specified for an interacting gas. It's just the size of the jump becomes smaller. In this case, there is no jump in the electron momentum distribution function, but there's a kink, there's a non-analyticity. So what happens is that, roughly speaking, the gauge fields leads to a breakdown of the quasi-particle idea in energy space, sort of like very much like the SYK model. You get no quasi-particle excitations, but nevertheless, they're sharp in momentum space. The idea of a Fermi surface is still well defined. Because what happens is you have these excitations which are not well defined, but they do have a definite charge. They're either quasi-particles or quasi-holes. And the locus of points in momentum space where your excitation change from quasi-hole-like to quasi-particle-like is the Fermi surface. Even though there are no particles, the Fermi surface is sharp. Yeah, this is going to be a topic that I will say much more about.
Oh, you're very good.
Yes, that's why I want to move on to other things to eventually get to this.
I once heard that this state is supposed to be described by a free massless fermion. Is that maybe that-
No, well, I mean, you can make an approximation and just treat it as free, but no, ultimately the quasi-particles are,
okay. Right,
It's-
it's a statement that it was some CFT and that the CFT was that of a free fermion. Maybe I'm just remembering.
no, I don't think so. This is definitely, the closest thing to this is an SYK.
I probably remember.
The closest thing to this is an SYK model, actually. It's strongly interacting as the SYK model. But it nevertheless has some sharp structure in momentum space, which you can investigate experimentally. Okay, well, I guess I will have to talk more about it. So what I wanted to talk about next, which is also a lot of fun, but something we can do next time. So another possibility for fermions, we go back to the beginning of the course. We said fermions form a Fermi surface, great, but what else do they do? Well, they form superfluids, superconductors. So what can happen in this case is that psi 3 fermions let me call it a superfluid because from a superfluid. Which means that psi 3 of P to the condensate of psi 3 of minus P, which is not equal to 0. Now, since there's no spin, this has to be an odd function of P. So it's not a D wave superconductor, which is even function of momentum. It has to be a P wave superconductor. And in particular, if you take what's called a Px plus Py superconductor, which is of this form, then the Bogoliubov bond bands of this superconductor, which we, again, you determine them exactly like we've done in previous chapters, they turn out to have a Chern number. I'll put Chern in quotes, but it's really like half a Chern number. I'll talk about this next time. So now you get a different type of topological state where you're pairing of these fermions and the bands have a Chern number. And that's what leads to a non-abelian state, in this case, the Moree state. Okay, and you can get, again, you put this in and you just go through all the tricks you have learned, you will get all the right properties of the Moree state. I'll say a bit more about that next time.
What determines whether it's superconducting or not?
Okay, it's definitely not a superconductor in the sense that you won't see a precision current. Because it may not make any difference.
These things count.
Superfluid, yes.
Right?
Again, that's depends on details. So there's some interaction between the fermions. It depends on which Landau level you're in. Depends on everything.
Actually,
Is there an attractive interaction?
is there an attractive interaction?
Well, so there is something called the Pcs instability that what we learned about, which applies for S-wave pairing when you have time reversal symmetry, where no matter how weak the attraction, as long as there's one, there's an instability to superfluid state. There's no such theorem here, but when you're broken time reversal. So you need some appropriate interaction. Okay, and in fact, it seems to happen in certain situations, not just in gallium arsenide, but also in graphene in recent years, where you do see. So this is now a regular fractional quantum Hall state in the sense that it's gapped. So this is a gapped FQH. It's fully gapped. There will be edge states. The edge states, because of this Bogoliubov Chern number, are Majorana fermions. They're not complex fermions, they're real because of this pairing, essentially. And the Majorana fermions is what leads ultimately to to so the non-abelian statistics appears from the fact that once you have a superfluid, you also have a vortex. So the vortex in the superfluid is a non-abelian quasi-particle.
Has this data been observed experimentally?
Yeah, well, okay. There is a fractional quantum Hall states observed at nu equals 1/2. The more reach state is the simplest possibility, but there are about 3 or 4 others. And I think, well, I'm not an expert on this, is a topic of, very hot current research. I don't think it's particularly been decided which is the right one. It may be more read, it could be something else.
I see. So some materials will give you the new 1/2 that you said before with mass density.
Yeah.
And other materials will give you the new 1/2.
Yeah, I mean, it could also be that if you went to very low temperatures, every material will go to this. Or some temperature range, you can ignore the pairing and then see the lower, you see the HLR state. But at low enough temperatures, it could well be everything will become paired and somewhat channel. But yeah, there are a bunch of other states, more complicated states, which also have Majorana edge states. And there's evidence for at least a Majorana edge, because that gives you a half quantized thermal conductance, which has been seen. Yeah, it's been seen. But there are also other edge states coming from the Psi1 and Psi2 fermions. So in this case, it's more complicated. You've got a lot of stuff going on. And there are other states. Yeah, I am not an expert by any means. But I think the current status is not yet clear which one of them has been seen.
Yeah, I know that a short while ago, I saw a paper that talked about the half integer thermal conductivity.
Yeah.
And I asked Greg whether this was proof that they found more reach state, and he said no.
Yeah, okay. Yeah, so he's being honest. That's correct. Yeah, that's my understanding too. Yeah. There's also analogs of the pairing in spin liquids, where you take a Z2 spin liquid and you pair this epsilon particles in this P plus IP state. And that's the Kitaev non-abelian state, which is similar, but its edge states are slightly different. Yeah. But everything can be, very compactly derived, at least these ones. The more complicated ones, maybe I'm not sure how to get them from the Cardano approach. Yeah. People are very fancy conformal with field theory ways of thinking about it. Okay, so yes, go ahead.
I just wanted to make a comment, question.
Sure.
When you here said that the size fill at Ni Landau levels,
Yes.
I was confused for a bit, but in the spirit of your derivation, you could say that if you did this mean field theory, you would have hopping Hamiltonians for the size, which would have Chern numbers.
Yes.
And Ni's could be interpreted as the Chern numbers of those filled bands.
Correct. Yes.
And then that would answer Tom's question about what the Chern-Simons levels are, because we would deduce them in precisely the way you said the other day, from the numbers of filled bands and from the gauge fields that couple to each species of fermion.
Yes, sure. I think that's correct. But I guess I was thinking about, well, what if you get to some physical response? The actual quasi-particle statistics is a bit more complicated, and how they couple to the external magnetic field and so on. Yes, but yeah, I think you're right. Yes, sure, you're right.
Is the discussion saying that the Chern-Simons levels would be like Ni for the Pi? And
yes, correct. Yeah, if you put it on a lattice, I mean, that's effectively what happens on spin systems on a lattice. Yeah, so there's okay, there may be a +1, sorry. Yeah, no, and the way I wrote it is correct. So N1 is just the Chern number. Yeah. So everything can go to Chern's insulators. We just replace the integers n with Chern numbers. Yeah. The number of Landau levels occupied. There's one caveat here in terms of the edge state, so they have to be careful about that. No, I think that's correct. No, it's fine. The number of edge states for each of them would be N1, N2, N3 also. Yeah. Which you can also see from the Halperin picture. You get N levels going to the edge. Okay, I've gone way over, so all right. Just a few more things to say, and then we'll move on to other topics next time.
And being infinity just means that Psi3 happens to have a band that isn't a Chern band. So say
Yes, right. Right, yeah.
Excuse me, Edward. There's an envelope with Kiara's name on it
Oh.
in the Princeton Rutgers office.
Oh, yeah, probably should pick it up.
Okay.
Fascinating as always.
Thank you.
Just mentioned offhand,
Yeah.
there was an analog to codes of the, with the.
That was just a throwaway remark. I don't know much about
That's a
it.
throwaway, okay.
Yeah, I mean, it looks like that, right? You
Right.
just take one and replace by 111.
Yeah.
So it looks like a code.
Of course, people looked at codes, quantum codes in Chern-Simon systems and
I don't know what's right. I think there may be some relation. But also all these gauge fields, Poitron construction are very much related to tensor networks. They also do
Yeah,
similar
sure,
things,
sure.
with extra degrees of freedom,
Right.
which are all related to code. So
Yeah.
there may be a way of unifying it more.
Okay,
elegantly,
I was
but
wondering if there was more to it than that.
there could be, but I'm not
Yeah.
aware of it.
Okay.
I think
Okay.
there could be.
Okay. I mean, the gauge conditions are really your stabilizer conditions, actually. They're
Is that right?
enforcing the code subspace.
Yes,
And,
yes, exactly. Oh, okay, now I know what a stabilizer is.
Yeah.
Yes, and they commute with everything else.
Right.
Okay.